Victory Power Hour. The first talk here is going to be by Lorenzo Perrone, who will discuss with us multi-messenger astronomy with Pierre Auger.
Okay, thank you very much for introducing me, and I want to thank the organizer for the invitation. I'm very happy to be here. Unfortunately, I missed the first part of the conference, but I'm happy to be here today. And we are now moving to the highest energy regime. So I want to define the context of this talk. So we are now dealing with this part of the spectrum for cosmic rays, so at the end of the spectrum. And the thing that I'm going to highlight here is the region that I'm going now to cover with some results in terms of ultra energy cosmic rays, but also in terms of multi-messenger physics, which is the main topic of this talk today. And so we learned a lot of things in the past two decades about cosmic rays, and we have now an unprecedented statistics and precision, but still there are open problems in our field, and as you know, the origin and nature of those ultra energy cosmic rays is still unknown at a certain extent. And the thing that we have learned, and I don't think I need to convince you about that point, is that to get a coherent picture of the origin of ultra energy cosmic rays, we need a multi-messenger approach. And here is an image of the multi-messenger astronomy landscape you know very well. This point, it's not very much updated, but this is not important. The important point is that as you see here, we see in this picture, in this frame, cosmic rays together with photons, with neutrinos, and observation of photons at lower energy. The important point is that we have always a strong interplay between the different actors on the stage here. And whatever we learn with this energy has some consequence and reflect also at lower energies and the other way around. So it's very important to explore and exploit all the potential of these. Even, and this is another very important point, in view of fundamental physics results or things that we might learn. And let me jump for a second here. I forgot to say that we are working here, operating here, at much higher energies than the one covered by the LHC experiment. And we can reach at the highest energy something like a few hundreds of TeV in the center of mass, which is much more than what we know from the man-made accelerator right now. So it's very important also in terms of potential for fundamental physics. Okay, the main actor, you know, and you have commented already many times on this, so I will be fast. You know, we have charged cosmic rays that are very nice. We have many of them, and we are measuring, keeping measuring them, but they suffer the magnetic field deflection. So the interpretation of the arrival direction is not always straightforward. And of course, in the field, we have also neutral particles that have a very good point in the sense that they point back to the sources, but photons have a limited horizon, and neutrinos are, of course, perfect candidate, but they are very difficult to be detected. And all of these things you know, and Marek has shown already this iconic plot here on the left, which maybe I will go there. So this plot here is showing the horizon for photons, and we are dealing with this region at the highest energies, and we have a very sharp window in which we can try to look for photons, for example, up to the closest galaxy here. And otherwise, I mean, this is opaque to photons, and but still open for neutrinos, of course. On cosmic rays, also the horizon for cosmic rays is limited due to propagation energy loss effect, and so about 100 megaparsec at the highest energies. And of course, our visible universe is limited in cosmic rays at extreme high energies due to this propagation effect. And this is fixed somehow, set somehow our limits for observation. Neutrinos are, of course, very, they can probe the deep universe, as you know. We can also have a look at neutrons that have a 15 minutes mean lifetime, but this is also, of course, can be converted into a limited horizon for observation. So I will try to comment on all of these messengers of the universe with different characteristics. How do we observe them? So we have built the largest cosmic ray observatory in the world. This is located in the southern hemisphere, in the Argentina, as you see here, close to the city of Mendoza. And you see here it's a very large array, 30,000 kilometers square. And here are some details about the detector that you might know, but let me go very quickly through features of our detectors. You see here, this is a grid of about 1,600 water Cherenkov station on a 1.5 grid. So each point here is a Cherenkov stations, and the array, the surface array, is overlooked by fluorescence telescope. We have 27 fluorescence telescopes altogether. 3 of them are watching at higher altitude. And the detector is also complemented by a radio array and muon underground detector to get a more hybrid, let's say, or more information about the detected events. So the observatory is running smoothly since 2004, and since 2008 with the entire full array in operation. And we have so far more than 100,000 kilometers square steradian per year of exposure for anisotropy studies, a little bit less for spectrum studies. And now, since a couple of years, we have started phase 2 of the experiment, which includes, I'm going to tell you in a while also, which kind of upgrade. And basically, the plan upgrade has been already installed, and the detector is in this second stage and is running fine. Okay, few slides, a few picture about our detector. Here is the fluorescence telescope site, including 6 telescopes, and we have 4 sites like that. And here you see the water Cherenkov on the ground, and I mean, this is a highlight on one of these, and some PMTs to detect the fluorescence light, and a cross-section view of the telescope. Now, I put here our highest hybrid event. Hybrid for us means that an event is observed simultaneously by the surface detector and the fluorescence detector. And not all events are like this one. This is our most beautiful ones, but of course it's good for advertising. And this is taken from our published catalog of 100 highest energy events, which you will find here. And most of this material is also available online and can be consulted if you want to play around with all the information given for these very beautiful high energy events. Now, the Pierogi Observatory is a 4-pi multi-messenger observatory in principle. This is a very important point because we have ultra-energy cosmic rays that I've mentioned already, and we observe them up to 80° in zenith angle, so it's the blue area here. And we have also very good sensitivity to ultra-energy photons in this zenith angular range here, and also to neutrino, which is extremely interesting because we are, of course, we are covering the highest energy regime with this observatory, and in different for different zenith angle, we have also access to this region here, Earth skimming slightly upward going neutrinos. I will comment on that, and this is actually our best and highest exposure channel for the search of neutrinos. And more recently, we have opened also a study for searching for upward going neutrinos in the fluorescence detector, which is a pretty new results I'm going to show you. Okay, how does it work? I mean, this is the concept, the way how we detect ultra-energy cosmic rays. You see here a reconstructed direction for primary particles and the shower observed by the fluorescence telescope. You see here the longitudinal profile. And basically, the energy of the primary particle is calculated calorimetric wise, in the sense that the area below this function is giving the energy released in the atmosphere, which is basically connected to the primary energy of the particle. So once you see this, you observe this, you can calculate the energy, and you also know what is the maximum, the position of the maximum of this, which is very sensitive to the mass or nature of primary particles. On the other hand, the surface detector is measuring the density of particles as a function of distance to shower axis, and we have found this density meter from the shower axis is a good estimator. But the good point that you can combine the two techniques and you can profit from the calorimetric measurement of the energy, which is basically model independent, and with the 100% duty cycle provided by the surface detector. Unfortunately, here the duty cycle is limited because we can observe only in the moonless and very nice clean night, which means 15% of the time, unfortunately. Okay, I'm going to show you a couple of slides also about our most important cosmic ray results before moving to natural, which is maybe interesting or more interesting for this community. But I still consider this part very interesting also because everything is interconnected, as I was mentioning before. So you see here the Auger combined spectrum. It's very nice, the precision, how we can measure the feature of the spectrum. So we know that the spectrum is suppressed at the highest energies. This was known and it's confirmed with the higher significance. We have seen the ankle and also indication of a second knee. And we have recently found also this new feature in this energy, which we call in-step around 10 to the 19 eV. So this is our current knowledge, which is very much improved in the last year, of course. And on the right-hand side of this plot, you see also the measurement of the mean X max. I remind you that X max is the position of the maximum of the shower in the atmosphere as a function of the energy. And this is very good because using Monte Carlo models, you can get an information about your mass composition. So, and we have now a very good precision also here, and we have indication that after this energy here, the mass gets heavier. So it seems that the proton fraction is getting much lower at higher energies, which is something we also not expect at the beginning, but it's very nice and important results. Another things that we can do once we know how the spectrum is and how the composition is, we can try to combine all the information and try to interpret our results. And the things that we have done is shown here and published also in a few years ago. It seems that we have a scenario which is rigidity dependent, which looks favored, as you see here, heavier and heavier nuclei that gets over with higher energies. And of course, this has to be also crossed with information about propagation. And right now, we think this is the most favorite scenario, but we still need more information about composition to disentangle properly a pure scenario in which the cosmic rays fuel is finishing in the sources from the propagation scenario. And this is one of the main goals of the Auger prime detector. Okay. Then let me also give a couple of information about astronomy that we are trying to do with cosmic rays. You know that cosmic rays are deflected by magnetic field. This deflection gets less important as you go higher in the energies. And so we try to investigate at higher energies the arrival direction distribution for our cosmic rays. And the most important results that we have found with the largest significance, it's now almost 7 sigma, is in the arrival distribution of our cosmic rays above 8 eV seems to be not flat in a right ascension. It means that we can observe a dipolar structure, anisotropy here, you see here in this plot. And this indication is very strong. And what is also very important is to look into the phase of the dipole, as you see here on the bottom right plot here. You see the phase of the dipole change promptly at highest energy. And this is a strong indication that this dipole is somehow suggesting us that the high energy part of our cosmic rays are of extragalactic origin. The three-dimensional reconstruction of the dipole is somehow anti-correlated with the galactic center. So it's more than 100 degrees away from the galactic center in this region here. And it's somehow correlated also with the local large-scale distribution of matter. So our extragalactic mass distribution is not uniform for us, of course, because our horizon is limited somehow. And then this is we see that this dipole is correlated with a matter distribution, and somehow telling us that cosmic rays at this energy are of extragalactic origin. We also try to look for sources at lower energy at intermediate scale, let's say not lower energies, intermediate scale. And there is still this region which is very interesting, the region of Centaurus A, which is populated by these three sources. And if we fixed in the direction of Centaurus A, we have a significance of 4 sigma post-trials. And we also try to match with some catalog and see if we have some excess compared to sources given in catalogs. For example, this one from Starbus seems to be the most promising one. And we have so far a significance slightly less than 4 sigma for this catalog, in which we take into account also the relative weight of the different sources. So now, do we observe only cosmic rays? The answer is not so easy. So we are sensitive to photon shower for sure. What you can see here on this left plot, you see a sketch of a shower induced by photon on the left, so the red one, and on hadron on the right, the blue one. And you see that the shower development for the two primaries differ. And this is because the proton showers or hadron showers somehow tend to release faster or earlier the energy in the atmosphere, because there are several channels, and therefore the maximum of the shower is reached higher in the atmosphere compared to the one that happened for photons. And because photon shower are much more constrained, so the interaction are mostly electromagnetic. The hadronic interaction for photons in this energy range is very, very limited, at a level of few percent. And this has also another important consequence, that the muon content of photon shower is very low compared to the one of hadron shower. So we have two important features that we can profit to separate photon from hadron, and these are the position of the X max and also the number of muons in the shower. Those prerogatives reflects into the shower shape, I mean, in the lateral distribution function, which is steeper for electromagnetic part and than for photon primary compared to the one of hadron, and also in the signal shape, giving let's say for hadron a much steeper signal in the detector compared to the one given by hadron, so by photon, sorry. So we have this let's say distinctive signature to find photons. So we start look photons in different way using the FD detector, a hybrid one, and you see here using Xmax and using a proxy for the muon content, and you see the two samples are well separated. And similarly, we do also with the surface detector, using the deviation from what we expect in terms of lateral distribution function and rise time. And you see that the samples are very well separated. So this allows us to look for photons, and this is the final, let's say, plot that is showing our upper limit. So the short answer is that we have photon candidates which are still consistent with background. So the things that we can do is derive upper limit for photons, you see. And what we have done so far is providing the strictest limits at energy larger than 0.4 EeV. So I'm starting from here down to here, you see. Our results are the stricter limits in the search for photons. And of course, this is also important not only for the search of photon itself, but also for fundamental physics, as I was pointing out before. Why? Because, I mean, having photons, for example, in this energy range would be a smoking gun for maybe exotic physics, because, I mean, a photon showing up at this energy either is produced by very close by sources, and we are not observing close by sources, or it's an indication of something strange going on with physics, like super dark matter models try to explain, for example, through the decay of particles that can produce photons, neutrinos, and cosmic rays. And so we are constraining such kind of models, and but this is not all the story, because it's important also for a study of mass composition, because we do expect photons being produced also by cosmic rays in the propagation. So, and hadron and let's say lighter or heavier nuclei produce different flux of photons. So if we reach this region here, we can say also something about composition, and we can already say that a pure proton scenario is disfavored also by the absence of, I mean, by our photon limit here. We tried to make also some targeted search. You see here, we look into the Hess measurement in the galactic center region, and we try to extrapolate this flux down to our energy. And so we could put also an upper limit on this measurement by Hess. We also look at different other galactic sources, and so far we have no evidence of nearby photon emitting sources in our energy range. And then we also try to make a follow-up of the gravitational waves events, and might be very interesting also for this community. And the thing that we did, we took 91 gravitational wave events from LIGO Virgo, and you see here them in a plot that is showing their distance and the significance or the let's say the localization of the sources here. So a very close by and very well localized sources sitting here, and the higher you go with the y-axis, of course, the localization gets worse. And then we have elaborated some selection criteria. Most of the sources are either too far or not so good localized. So most of them were not considered in the follow-up, but we selected 7 event and altogether in class 2 and 3 in class 1, and in 2 different analyzed in 2 different time windows. This is a longer time window. So I mean the time windows are defined here. So a short one is 1,000 seconds centered at the time of the gravitational wave, and a long time window is defined as 1 day after it. So we looked at these specific sources that were close enough and were potentially interested for us because the localization was good, and we could put some upper limit on their photon fluence in our energy range. And this is the famous, you know, candidate from gravitational wave, but we don't observe photons in our range. Okay, and neutrinos now. This is also very interesting and important channel. We have a very good sensitivity, in fact, for neutrinos. How do we observe, or we plan to observe neutrinos? So we have different channels, as I was mentioning before. We can observe neutrinos which are almost horizontally or even a little bit upward going. Why? The reason is mostly because we need to separate them from the background of cosmic rays. So the point is that neutrino can interact only weakly with the matter. So they're basically, the atmosphere is basically not influent for them. And so you have no way to separate them from the cosmic rays unless you go on very inclined event where you are sure that hadron showers are now very old, let's say. So there is a very small content of electromagnetic particle, and you see a signal like that for hadrons. If you have a neutrinos which is interacting close by to your detector, you will see it showing up like a signal very rich of electromagnetic particle, like here. So you have a very strong indication that let you separate hadron from neutrinos for very inclined events. And similarly, also for Earth skimming neutrinos, which may produce a tau in the ground, and the tau is emerging and decaying and producing a shower that could be observed up to 95 degrees in the zenith angle. The dominant channel, in fact, in our exposure is from neutrinos coming from upward going Earth skimming tau decaying over the array. So once we have elaborated this technique for measuring neutrinos, we can build an observable here, which is based on the feature I was mentioning before. So we are looking young shower versus old showers, and in this plot here, you see what is our rejection capability, which is very, very high. So this search, unlike the one for photons, is basically background free. So we have an expectation of less than 1 event. If we have a neutrinos, it will be a breakthrough here in this case, because the background is basically 0 for us. So this is a very important point to be highlighted, I think. And so far we have no candidates. This is the thing that you know already, of course. And we could set some upper limit in terms of diffuse flux, you see here, them versus the results from IceCube, for example. And as you see here, and as is going to happen also for photons, we are very close to this region that we call cosmogenic neutrinos, so neutrinos produced by cosmic rays themselves. We know that there must be a floor of neutrinos produced by cosmic rays, and we are very enriched of this region. And so we can say very soon something also on the composition of primary cosmic ray. So the other very interesting point, especially for this community, I think it's looking for point-like sources and coincidence with gravitational wave. Many things has been done already by Marek, so I thank him for that. So I will be very fast on that. I mean, here is an important plot that tell you basically how much is the sensitivity in terms of declination as a function of time. So how many hours, let's say, you can observe a specific declination in the sky. And we were very lucky with this GW170-817 because it was ending up right in the in our highest sensitivity channel. And so we could say something. And of course, we don't see any neutrinos, but we could set an upper limit just because this event was falling into the right position at the right time, which is not really automatic. So, and okay, this was, you know, this event. And so you see here our neutrino search here in this Earth skimming channel here. And so we could set this limit. They have been presented by Marek already, so I'm not going to discuss them further, but they are the most stringent limits in this energy range, of course, in these different time windows, plus minus 500 and 14 days after, as Marek was commenting. The other candidate is the Texas sources from IceCube. Also, this one is a very famous one, and so you have heard for sure about this event many times. And so we went also in our data looking for that. We were not so lucky for this event. As you see, the event was falling in this region where our sensitivity is at the minimum, I would say. So once we were lucky and once we are unlucky in this case, so we can't say so much. Nevertheless, we have still some residual sensitivity, which is here shown and allowed us to set upper limits that you see here in this plot where you have the observed flux, the neutrino event, and also our upper limit in terms of in two different time windows again, and also calculated for gamma from that direction. So this was the most recent result for the field. You know about this famous event that has been reported recently in a Nature paper by the TM3-NET collaboration. Then the question is, are we lucky with this or not? So the answer, unfortunately, is not. I mean that this event was not visible for us because the zenith angle was too small at about 30 degrees. So it was not matching any of our declination band in which we are sensitive for the neutrino search. And okay, bad luck. But anyway, so we keep tuned for the next nice event. And we also made a follow-up for gravitational sources from LIGO Virgo. And we set up some fluence upper limit, combining all the results together after inspecting 93 mergers from the LIGO Virgo results, catalog results. So also we made cross-checking with other experiments. This is also important to be highlighted in terms of interaction in the multi-messenger context. We are in contact with IceCube telescope array, Antares, and we published together this map of the sky. Everything is compatible with background, unfortunately. And we were looking also for neutrons. I mentioned that neutrons are decaying after 15 minutes, and this is translating into an energy-dependent horizon, which is anyway rather limited for us. It's about the scale of our galaxy. And so we could set, so we couldn't find any excess in cosmic rays in the direction of these sources that we were testing, and we were setting upper limits. So this is part of our program. And the last thing I want to mention here is that we recently have started also a search for upgoing showers after the claim done by the Anita balloon experiment that somehow they were observing strange events with strange polarity that were not really understandable in terms of radio standard signal from ultra energy cosmic rays. So there was a long debate in the community, and so we are starting searching upward going neutrinos with the fluorescence detector, and this work has lasted a long time. At the end, it's been published, I mean, it's been accepted for publication recently, so you will find the results already very soon. And we could find one candidate which is consistent, again, with our background. I don't go into the detail, but this is a good thing that we might use for discussing later, if you want, and provide more details about this. The important point of this analysis is also that, again, from the physics point of view, there is no reason why in the standard model we should expect a tau emerging at 10 to the 17 or 18 eV from the ground, because the tau would be absorbed in the Earth. So the things, I mean, having an upward going showers, this energy is kind of smoking gun again towards some new physics. For example, physics beyond the standard model. And so this was an exercise done to understand how much we would have need to change the deep inelastic cross-section to observe an event. And so you see here, we are providing upper limit for that. And the best upper limit would be for 3% cross-section with respect to the one predicted by the standard model in this energy range. Prime. So we are on the good trail for prime. So we are going to run 10 years longer with our upgraded detector, which includes a scintillator layer on top of each water Cherenkov station. We have a faster electronics, which is helping improving on signal characterization and has a higher sensitivity. We have added low gain PMT to study shower closest to the axis, and we have added radio antenna for horizontal event and neutrino study, which are really interesting also. And we have many more muon detector that, of course, can provide a direct measurement of muons, and which is very important given the muon excess problem that runs for many years. And let me also advertise, we have a very nice open data. This might be very interesting for, and I'm really done, very interesting for this community. We are going to release, to increase the fraction of release data from 10% to 30%. I mean, it's not the end of 2024, sorry, here. It's later this year. It's a bit postponed, but I mean, you can keep tuned on this website if you want, because there is a lot of material, a lot of stuff also for outreach, and it's really nice. So please have a look at that. And we also recently gained the cover of the APCJ journal with our publication on open data, which is a good result. So here are the conclusions, which I think I can leave it there for you if you want. And that's it. Sorry.
No need to apologize, just means there's fewer time for questions.
Okay.
Any questions?
Thank you for the very nice talk. So given that pure proton composition is ruled out, so what's the current status? What can you say on cosmic ray composition in terms of higher Z numbers?
Yes, maybe I can go back and show you with a little bit more time this plot. Sorry for flashing all the slides like that. Okay, so this is our latest publication. And you see here, I mean, this is the position of the X-max, which you can interpret in terms of using models, of course, in terms of proxy for mass composition study. So what we observe here is that while at this energy, we still have predominantly light components, as the energy increases, the composition seems to be heavier. And we also have calculated the fraction of heavier nuclei that we expect, and we have something like helium and CNO particle raising progressively with energy, and we have a very small fraction of iron anyway. But still, the stuff is getting heavier, and the important point is not only the min X max, it's also the fluctuation. I mean, the sigma, so the spread of the X max, which is getting smaller. And this is what you expect if the composition is getting heavier. So we have a really strong indication. And the very new part here is that we could extend the measurement at very higher energies, profiting from the statistics of the SD detector using neural network approach, so deep learning. And somehow we were training the analysis for SD, which is not so, the resolution of X max for SD is not that good as for FD, but you can train a neural network and you can make a measurement of SD and you can use the X max scale of the FD also for this case, because we can use a hybrid event to correct somehow. And the shape that we find with SD up to here is totally consistent with what we get at lower energy. So the picture seems to be this one. And
Got time for one more quick question if anyone has one.
Thanks for the talk. Could you say something about what type of data you release and what it could enable?
yes. So we have a lot of data. Maybe we can also discuss that if you want, because it's a long, but okay. We have different data sets here. We have data set from the hybrid detector, which includes the FD part and the SD part. It's like a JSON file, which you have the information of the individual event, and you have also the SD traces, if you want, the traces of the event. And you have also some software and some also application that are reproducing our main measurement. You can find application for measuring the spectrum, the anisotropy and cross sections or whatever. So all the analysis that we done are somehow provided for an external user using only a fraction of 10% so far. But this fraction is going to be 30% very soon. And so you really have access to, I mean, you can do physics. We have already people publishing real physics journal using our open data. So we have 3 or 4 papers that has been published using the open data. I mean, 30% is very close to what the telescope array experiment in the Northern Hemisphere has as the whole amount of data. So it's really, I mean, 30% will be reusable. I mean, the idea behind is that we want to deliver our effort to the community. Maybe somebody has a nice idea outside of us, I mean, and can do something with our data. At the end, it's money of the public, of the people. So we want people get access to those information.
Good argument to make.
Yes. I mean, my personal opinion, and I think, oh, sorry, it's too late.
Discussion later. You can point your finger later in the maybe discussion session. So Lorenzo will be up here again later.
Yes.
So
I
let's
would-
thank Lorenzo again.
Okay.